Hi, my name is Alyssa Roden from the Southwest Research Institute in Boulder, and I'm talking to you today about Europa and Enceladus, two active ocean worlds. Here we see two worlds that have a lot of similarities. First, we know that both Europa and Enceladus have global liquid water oceans under their icy shells. We also know that these two moons orbit in slightly eccentric orbits around their giant planets, and they both exhibit some recent tectonic activity. However, as we've looked deeper into these two moons, we find that they're really quite different. And one reason that they're different is something I like to point out right here at the get-go. Enceladus is a lot smaller than Europa. Here it is shown at its actual relative size. So the processes that govern these two bodies are going to be different because a lot of them depend on size. So let's start with Europa. We know that tides dominate a lot of what goes on within Europa. So the way this works is that Europa goes in an eccentric orbit around Jupiter, meaning every 3.5 days, it goes from being very close to Jupiter to being rather far, and that causes a bulge to raise and lower throughout each day and also shift in its longitude compared to the direction of Jupiter. Similarly, we think that Europa's spin pole is slightly tilted, called an obliquity, and that slight tilt causes the tidal bulge to actually shift up and down across the equator throughout each orbit. And all of this motion, this tidal flexing, creates heat and stress, and that stress may be able to crack the surface. So by comparing the orientations and locations of fractures with our predictions of tidal stress, we can start to learn about the interior, the orbit, and the ice shell processes. When we look at just obliquity stresses here on the left, we see that throughout an orbit, the stress orientations and magnitudes can change. So each of these little lines is one of the two principal stresses that's associated with eccentricity tides. And throughout the orbit, they can change from being in tension, which is opening, to compression, which is closing, and they can change in the direction of the stress. And one thing you'll notice is that these stresses are symmetric. So whatever is going on north of the equator is mirrored south of the equator. On the right, we've shown it a different way. So here we went through each location, the entire orbit, and said, what is the peak stress magnitude, regardless of what time it reaches that magnitude? And we created contour plots of the stress magnitudes. And so here you can see, again, that the stresses are symmetric and that they are not uniform across the whole globe of Europa. When we add in that obliquity here, about 1/4 degree, it breaks that symmetry and creates different spatial patterns depending on what direction the spin pole is pointing. And here I've shown just two examples at spin pole direction of 0 and at 90, and you can see that those higher stress lobes shift off of the equator. And we found that of all the features on Europa's surface, it's cycloids that most clearly record the patterns of daily varying tidal stress. So cycloids are shown here in the white arrows. They are arcuate fractures linked by cusps. And we've known for a while now that we can recreate these shapes by looking at how the orientation of stress changes throughout the orbit. And so I'll run this little movie, and you'll watch the stress vectors changing in their magnitude and direction, with cusps forming when the stress actually gets too low to continue propagation. And then the next orbit, as the stress increases, the direction is different, and so we get that cusp. We also know that equator crossing cycloids cannot be matched by eccentricity alone, and that's because, again, the eccentricity stress field is symmetric. However, when we add in a combination of eccentricity and obliquity, we find that we can explain really all cycloid shapes. So here on the left, I'm showing the same image of 3 cycloids in the southern hemisphere, and below that, a suite of cycloids that we've identified near the equator or even crossing the equator. On the right, I'm showing some of our best fit models using tidal stresses and a mechanical model to fit the paths of these cycloids. So here, the black dots are the data that we took off the images, and the orange lines use a model of eccentricity and obliquity. And you can see that both of these can be fit pretty well. We also found that if we add a small physical libration, so a wobble of Europa, we can get better fits, and it seems to reduce the amount of longitude shift that we have to assume. So when we match these cycloids, we have to move them from where they're observed. But on the right here, I'm showing the very best fit we've ever achieved, and it used a model that included eccentricity, obliquity, and libration. And this fit only required a 3-degree longitude shift. And that suggests to us that as we get better at approximating the stress field and also the mechanical model of cycloid formation, this need to shift things in longitude is kind of going to disappear. Another thing that eccentricity and obliquity can explain is the asymmetric patterns of where cycloids are located and also the orientations right at the cusps. So on the right, in the upper panel, we've mapped cycloids in all the regions where we have decent imagery and can actually do this type of mapping. The green dots signify where we saw a cusp, and the red lines connecting the cusps are the cycloids. And here we've also added some blue shaded regions to show areas where chaos features have really dominated the region. So even though we don't see a lot of cycloids in that area, it doesn't mean they didn't form, it just means they've been obliterated since they formed. So what we did was we used a model that had eccentricity and a 1/4 degree of obliquity. We allowed the spin pole to vary, and we found that we can match the orientations of these cycloid cusps using this tidal model. We could fit 85% of them, and we don't have to shift them anywhere. Some of the cycloid cusps that we fit would imply a pretty low stress, so those ones we're not certain about, but the vast majority fit at relatively high stresses. We did find that stress had to be increasing when formation occurred. These fractures don't fit if you just wait until the very largest stress throughout the day. And that's consistent with some other results that I'll show you. Another thing that eccentricity and obliquity can explain really well is the orientations of more linear fractures, as well as the distribution of right and left lateral strike slip motion that we see along those fractures. We can also predict why certain fractures tend to have more offsets than others, and that has to do with their orientations. So on the left, I'm showing in panel A, a map of strike slip faults that was taken from a paper from quite some time ago. And then in panel B, I've shown a zoom in on part of it so that you can see how these features are offset along the different faults. In the middle panel, we've aggregated all of the mapping across all of these images, and we've binned them by latitude and longitude. And so red lines indicate left lateral offsets, where the orientation of the line shows you the orientation of the fracture along which this offset occurred. And the blue lines represent right lateral offsets. And what you'll see is that in both of these longitude strips, we have regions where we only see right lateral faults, regions where we only see left lateral faults, and then regions where there's a mixture. And if you use an eccentricity stress field, it would predict these mixtures to be centered on the equator and symmetric north and south. But when we add in a little bit of obliquity, we find that we can predict exactly where these regions are. So on the right, we've used our tidal model, and we've found that orientations that would produce left lateral offsets are shown in black, and those that produce right lateral offsets are shown in gray. And again, we can match pretty much exactly where the mixed regions would be using this model. And finally, some recent work, we took that same stress field that we used to match cycloid clusters and their cusp orientations, and we compared it to some interesting features pointed out by Schenk et al. 2008. So there are these curvilinear depressions, which are shown by the black lines here. And Schenk et al. Found these features and fit them to circles because they seem to be curved. And those little black circles that we've marked on this contour plot show the locations of the best fit circles that they report. So we haven't tried to fit these features at all. We haven't varied the eccentricity or anything beyond what we were already doing for cycloids. And we found that they actually match really well. The center points fall right within the center points of the high stress regions, and the features roughly correlate with the shapes of the contours. There are some new features that have recently been identified in Schenk et al. 2020. There are no specific age relationships that make it clear that these all formed at the same time or from the same process, but as they are concentric to these features I've shown, we expect that obliquity tidal stress probably had a role in forming all of those features. Moving away from tidal stresses, we also see evidence of large-scale ice shell processes on Europa. So reconstructions of numerous regions have shown that some areas move as rigid plates, more like on Earth, but that plate motion is not global, it's episodic in time, and it's not really active today. We also found that some of the smaller features on Europa, pits, domes, and small chaos, appear to be anti-correlated with plate motions. And on the left here, I'm showing a map of a Greenberg et al. 2003 paper where they mapped pits, spots, and domes and found that they are clustered in location. So there are regions where we just don't see very many of them. And what we're finding now is that the places where we see many of these so-called microfeatures are also the places where we don't see rigid plate motion. So it suggests that there's some kind of overall process of either thermal transport or liquid in the ice shell that's being accommodated in two very different ways. One that leads to these small microfeatures and one that leads to more broad rigid plate motion. And finally, we can think about how Europa's overall evolution affects its activity. So over time, Europa's eccentricity varies periodically, and that can lead to times of enhanced tidal stress and heating and times of reduced tidal stress and heating. And this cartoon mentions the range of eccentricities can actually be quite high depending on the model assumptions. The reason this is important is that when you reduce the amount of heat that's being produced in Europa, you can freeze out some of that ocean, and that generates cooling stresses, which are really, really large, much larger than the daily tidal stresses, but they're uniform in orientation. So that means that the tidal signature can still be really prevalent, even if it's a combined stress field that's creating fractures. The opposite is true when the heating is enhanced. So when the eccentricity is high, you can actually melt the shell, and that puts the surface into compression. And it's unclear at this point what surface features, if any, form during those epochs. And we're starting to look at how Europa's ice shell thickness itself can vary in these different time periods. And in doing that, we've done some more sophisticated tidal heating models. And what we're finding is that Europa's equilibrium ice shell thickness at its current eccentricity is only about 7 kilometers. That's down from about 30 kilometers from some older models. We're also finding that cooling preferentially leads to pretty shallow cracks. And so there's some real potential here to perhaps crack through the ice shell or to create more conduits between the liquid water and the surface. And that's really what we're looking for here, is how heating and cooling epochs can get water into the shell, because we see a lot of surface features that have been attributed to liquid water, though none definitively. But getting liquid water up into the shell is a challenge, and we need a combination of pressurized ocean water during freezing, but also fractures that can penetrate downward. So this is a complex system that we're still trying to puzzle out. Some conclusions about Europa. So we see that Europa's whole ice shell is continuously being processed through tidally driven fracturing, thermal processes, and large-scale ice shell motion. We also know that Europa's non-zero obliquity affects the formation of fractures, including straight and cycloidal lineaments, strike-slip offsets, and maybe these semicircular depressions. We also know that ice shell thinning and thickening due to eccentricity variations are likely important processes for breaking the ice shell, because they can produce these large additional stresses and ultimately driving the activity that we see. And the vast majority of Europa's fractures indicate that they have not moved since they formed. So this really limits the potential history of non-synchronous rotation or polar wander, which have been previously proposed for Europa. So now we're going to look at Enceladus. And we can see some differences right off the bat. So Enceladus has a global ocean, but it only has regional activity. The North Pole is heavily cratered, has relatively little tectonism. The leading and trailing points along the equator actually have some older terrains that have fractures, but they also have some craters. They're not the youngest features on Europa, and we think that they're basically defunct. And finally, the South Pole is heavily tectonized. There is 0 craters, which means that the surface is super young and it has active eruptions. We think that part of the reason for these differences is that the ice shell on Enceladus has variable thickness. So we have a lot of data now that suggests that the ice shell is thinnest at the South Pole, maybe only a few kilometers thick. It's thicker at the North Pole than the South Pole, and it's probably actually the thickest at the equator. And some recent work has shown that a locally thin ice shell could enhance tidal stresses at the South Pole by an order of magnitude over the ice shell if you assume a globally average thickness. So this could really get us to the point of having tidal stresses that can crack the shell. So if Enceladus is fractures formed from tidal stress, then it's these differences in ice shell thickness that may explain why we see tectonic activity in some regions and not others. So we looked into that in some detail, specifically to look at whether the tiger stripe fractures, these young parallel fractures at the South Pole, were formed through eccentricity tides. So on the left here, I'm showing the data we collected. So we took measurements at about 2,400 locations along the 4 main tiger stripes, measured their orientations, and we plotted them here in this histogram. And you can see visually that those 4 black lines are pretty parallel, and that bears out in the histogram where we see a pretty strong peak at about 130, 135 degrees. And then in order to try to match that, we looked over a broad range of interior structures and a few different failure criteria and tried to predict where a tidal stress field would, what orientation it would create at each of these locations. And so in the middle panel, I've showed a sample of that. So here we have tidal stress over one orbit. The x-axis is the fracture orientation we would predict, and the y-axis is the stress magnitude. And here at the particular location we computed stress, the observed orientation of the fracture is about 50 degrees. So you can see that if we assume a failure stress that's close to 200 kilopascals, and while this stress is increasing, we would match that orientation very well. Whereas if we assumed the peak stress or some number like 100 kilopascals, we would not match that very well at all. So in the right panel, we've actually created histograms from this predictive data where we selected different failure thresholds. And you can see that the blue is the same as in the leftmost panel. The orange, where we assume failure at peak stress, really doesn't fit the observations at all. But when we start to make assumptions about failure occurring in the second half of this increase in stress, we actually match them really, really, really well. So we think that this is strong evidence that the tiger stripes were formed from tidal stress, that tidal stress governed the orientations, and similar to Europa, that failure seems to occur while stress is increasing near the peak, but not at the peak. We also know that eccentricity tides control Enceladus's plumes. So you can see again the fractures there on the right, a nice graphic image captured of them erupting on the left. And this plot shows the eruptive output wrapped on Enceladus's orbital phase. And the fact that we see a consistent pattern to the increases in jet activity tells us that tides have a role in this process as well. Although the mechanics of how the fractures open, close, and bring liquid water up is really not well understood. And so we've had a bit of trouble matching exactly the timing of these eruptions. So one way we can start to think about Enceladus and all of the different observations that we have is that Enceladus may be a moon that transitioned from a frozen world to an ocean world. And the reason we think this is that in the left panel, we see tidal heating in a world where the ice shell is in contact with the ground. Okay, so there's no ocean in this model. And tidal heating in that case is concentrated at the equator and at specific longitudes. And this correlates really nicely with the places where we see older tectonized terrain. So if Enceladus was at one point completely frozen, these are the places that would have melted first. And then on the right, we see tidal heating in an ocean-bearing Enceladus where the pattern is completely changed and all the heating is concentrated at the poles. So if we had a transition from one to the other, we would change the places where heating occurs. And as hotspots can lead to locally thin zones where tidal stresses are enhanced, we may also be able to explain why we transition from tectonized regions at the equator to tectonized regions at the pole. Now, of course, a big question is why only one pole is active. But we may be seeing something where the North Pole is just taking its time and is actually thinning and will become active. Or it may be that once we fractured through the ice shell at the South Pole, it changed the stress field enough that you're not going to see the same type of activity at the North Pole. We also know that a late ocean on Enceladus is possible. Some pretty complex thermoorbital evolution models that co-evolve all 5 of Saturn's mid-sized icy moons can produce a late ocean in Enceladus due to mean motion resonances with other moons. And on the left, I've shown the processes that were included in that model. Of course, even a complex model has some limitations. So we can't say for sure what evolution Enceladus underwent, but we can say that a recent ocean is possible. And this corresponds well with some evidence of heavily relaxed craters, even far from the South Pole, and that indicates an epoch of high heat flow, such as would occur if the eccentricity was temporarily raised due to a resonance passage. So this is really helping us to understand how Enceladus formed. So here we have our two ocean worlds with very, very different histories. On Europa, we see chaos, pits, domes, things that suggest liquid water or some kind of thermal transport within the shell. And we see that behavior globally. We also see bands and rigid plate behavior that's associated with some kind of large-scale ice shell motion. We see cycloids, which are clustered, and linear fractures, which appear ubiquitous. And we see no modified craters. And we don't really have a good reason why those craters that we observe on the surface are not modified. But all of this points to a Europa that has continuous geologic activity that's driven by a combination of tidal stress, changes in ice shell thickness with time, and some overturned processes going on within the shell. And then we look at Enceladus, which has no chaos, pits, domes, bands, or cycloids. It has localized tectonic activity spaced in time, including some ancient terrains. We know that eccentricity-driven fractures have formed on Enceladus, but they have a really different sort of character to those on Europa. We don't see cycloids and we don't see them globally. We also see tidally driven plume activity on Enceladus from this very consistent plume set, and we don't see that on Europa. And we see very heavily relaxed craters, even far from the South Pole, and a measured high heat flow at the South Pole. And that's quite different from the non-modified craters that we see on Europa. And so for Enceladus, we think we're seeing a moon undergoing a secular change in its geologic behavior that was triggered by melting and ocean formation and is now largely controlled by tidal stress and also global ice shell thickness variations. So this leaves us with some interesting open questions. First, what is the failure strength of these ice shells? Are they really failing just from tidal stresses, or are we adding cooling stresses in the case of Europa, or enhancements from these locally thin regions like we see on Enceladus? And does that lead to a mixture of shallow and deep fractures that might create a complex plumbing structure within these shells? Both moons have really densely packed fractures, as well as less numerous, more ordered fractures. And we're not really sure what causes these different types to form, why they seem to both be in play, and display such different spatial characteristics. We don't quite understand yet what the role of physical libration is on these worlds, so we suspect that it's going on Europa. It is measured for Enceladus, and it won't change the tidal stresses very much from the eccentricity stress field, but it could maybe help us understand why fractures form in certain places and not others, and why plumes erupt at particular times. We'd like to know whether there are pathways between the ocean and the ice shell on Europa, and how the conduits were first created on Enceladus. We'd like to understand what triggered Enceladus's transition to an ocean world, if that's indeed what has happened. Is it periodic? Is this the only time it's ever happened? And how will Enceladus evolve from here on out? Will it become something like Europa with this sort of continuous geologic activity, or will it just become a defunct frozen world once again? We don't have a lot of information on the thermal processes that are active on these moons, but they seem to have manifested very differently, with things like chaos and pits on Europa and high heat flow and relaxed craters on Enceladus. And finally, we'd like to understand how habitats might have evolved through these freezing and melting events. And with that, I'll finish, and thank you so much for your time.